Yeah. So a lambda term would be just a variable. So yeah, I first thought that a lambda term would be something that would have a lambda to it, but that's not true. That's not true. We can see in this paper by Robert Harper, variable x. And also this, for the time being, it is best not to try to impose meaning on lambda terms, but just rather concentrate on their definition as pieces of syntax. So the idea is that the lambda calculus is a system of functions that may be applied to one another. Well, of course you're going to apply them to one another, right? Of course you are going to apply lambdas to one another because it's all you got. Right? Now look at this. True and false, 0 and 1. So true and false is defined with a constant combinator. Constant combinator. So constant combinator would be a k. Right, so we have a lambda term. A lambda term is just an x, but I guess we cannot use the x here. But what would x mean actually if we don't have values? That's kind of like, what would a lambda term x mean when we have no values to provide it? When we encounter a lambda term like x, its meaning depends on context. I think that's the problem sometimes. The scope, we understand something, but it's something that we understand. And it's kind of something that we come like, what's the thing? With assumptions, right? Like this x, I was kind of confused. How would the x be a lambda term? When x appears in a lambda term, it acts as a placeholder for something that might be provided later in the absence of an actual value. X simply represents a possible value. The lambda term lambda x dot x defines the identity function. Without applying lambda x to an argument, x is undefined. The term remains abstract, waiting for a value to give x meaning. But we have identity function and we have a lambda term. So what's the difference between a identity function lambda x dot x and a lambda term x? The key difference between lambda x dot x, the identity function, and the lambda term x lies in their roles. So the identity is a function abstraction. It has a binding operator lambda, which defines x as a parameter. And the body of the abstraction is x. which is returned when the function is applied. Lambda x dot x defines a function that when given an input returns that input unchanged. Lambda x dot xy reduces to y. So in SML we would call it, I guess we would call it val identity. Val identity. And fn x x. And we have an identity function fn from any type to any type, so we can give it whatever we want. I guess we could give it another function. So identity 2 is 2. It gives us back 2, but it does not give us back the function. I guess that's the difference between the constant combinator and the identity combinator. It's a combinator because it has no free variables. Now, what are free variables? All the variables are in the scope bound. So we have the x, which is bound to the x, and it's self-contained. As you can see, you can apply the identity, but the identity itself, the definition is self-contained, right? Because we have the x, which is bound to the x. So whatever we give it to, it gives us back. Now, the k combinator, is fn x. Well, no, it's fn, it's lambda x, so you can read fn as lambda, is lambda x, lambda y, and now x, error, syntax error, fn ida, darrow, syntax error found. Oh, so it's val k, fn x, fn y, x. So now we have a constant combinator. Now what's a constant combinator? Sure, it's a constant, but how does it work? Because it's not just that it returns the first thing that we give it to. We see two functions here, fn x, fn y, and then it gives x. It's represented in curried form. Right, but why is y already declared in advance? It seems like y is declared already in advance. So a constant combinator is something. I guess you could say, how do you define a constant? A very crude or like naive idea, it would be to conflate it with the identity function, because identity function could be seen as some sort of constant function, right? I guess you could say that. It's not, but I guess that was my first naive idea, is that the constant function, well, it remains constant, but I guess you would say compared to what? So you could say then that the constant function, or the constant combinator, remains constant no matter what changes on the outside. And that may be the difference from the identity function, because at first I thought that the constant function would be something that remains the same remains the same, but how? Constant function. It's kind of, you know, you can really gloss over it and say, sure, it's a constant function, but it's somehow, you feel a profound insight on the constant combinator and its relationship to the identity function. So we have the identity function, right, in the lambda x dot x. That's like the basic function, right? It gives us the same thing. Wait a second, do I have, let's call it id fnx fnxx, right? So id2, it just gives us back whatever we give it. Id hello world. Operator is not a function, bad instantiation operator. And what's happening here actually? It's interesting. Id. Oh, what did I do? Id hello world. Maybe because of that 0. Yeah. So you could do id. I guess you can do it like this, right? Could you do id times id? Operator domain? No. But you could do like this, I think. So how do you apply identity to identity itself without giving it something? Value restriction are instantiated to dummy types. Yeah, it would work if I do id a. Right? No, it didn't work. How do I, yeah, let's check this. It does not modify its input, but simply returns it as it is. So the identity, yes, does not modify it. That would be one of the differences between the combinator and the identity, because the combinator somehow modifies the input. Maybe that's why the identity is so basic. It does not modify the input at all. It just gives back what you give it to. So its result depends entirely on the input. A lambda x dot x a evaluates to a. So in that sense, I guess, each variable in the lambda calculus is a lambda form term, but maybe that's not the correct, yeah. The identity function is a mirror. It adapts to its environment by reflecting whatever it encounters. Its behavior is inherently tied to what is applied to it. Now the constant function or constant combinator, lambda x, lambda y, x. The constant combinator fixes its output to a value x and ignores any other input. But it's interesting that you would, I guess you would first think that maybe it's lambda x, xy, you know? You would think that it's almost like lambda x dot xy, and then you give it something and it returns. Well, you would have to give it two things. Yeah, this is about the curried form. Yeah, I think the confusion comes from not expecting the curried form of the function application. So one could expect something like lambda x dot, let's do it like this, lambda x, or I'll do it actually in SML, fn x, I guess you would expect something like fn x, whoa, wait, I could actually lower the quality. Yeah. Encoding must be, yeah. So I think the confusion comes from not expecting the current form of the function application. So one could expect something like fn x and then x and then y, even though this is wrong, right? Right? And then like you could think to put this like this, and then you give it what? You give it something and returns the same thing. This was my first really dumb idea, but this looks dumb because I guess this comes from not thinking how would one actually define a constant function. So it's not that you are looking from inside and saying I am staying constant, but is more like if you give me two things, I will only choose the first thing. Yes. One more thing is, I guess another confusion comes from thinking a constant function is something that will remain the same within the program duration. But here, the function can take the two arguments any number of times. So it's like, how would you say it? It's like, it's more about that it always takes the first argument, and not that it somehow stays immutable forever. Oh, I'm still sick. You've hit the nail on the head. The confusion stems from a couple of expectations about what a constant function should be and how currying influences its behavior. Let's unpack this systematically to clarify these ideas and demystify what's going on. So let's check out some examples. In a non-curried mindset, one might expect the constant function to look something like fn x, fn y, x. Here x and y are handled together and the function explicitly returns the first argument x. This style feels more intuitive because you think of the function as receiving two arguments at once. Yes, but first I thought, well, yeah, GPT is good for this, you know, giving somehow more value to the context at place, but receiving two arguments at once. Oh yes, actually, it's not receiving two arguments at once. So it's not just that it represents the evaluation in the correct form, but also receiving the two arguments does not happen at the same time. So currying is used by default, but not just when you produce an evaluation, but also when you receive something. This makes sense actually. So multi-argument functions are represented as a chain of single argument functions. So f of x and y is represented as f of x, f of y. fxy. The currying transforms the constant combinator lambda x, lambda y, x into a sequence. First fix x, the first argument, then create a new function lambda x which ignores y. So if you think of function application like k2y, you see that k2 becomes a new function. Lambda y is 2. The abstraction feels dumb or anti-intuitive at first glance because the structure isn't about keeping x inside the function, but almost incrementally building behavior. The constant function isn't about immutability or staying constant, in the sense of being unchanging over time. It's about choosing the first argument every time. So the constant combinator isn't introspective or self-aware, I'm constant. Instead, it's like a decision maker, giving two options. I always pick the first. Yes. This makes the constant function inherently relational, not introspective. It's not saying I refuse to change, but rather I have a rule that always prefers the first thing, no matter what comes after. So that's the idea of what I was kind of, so like val add, okay, val add fn of x, right, fn of y, x plus y, right? So this is the add function, and then add 1 and 2, we get a 3. And let's do it again. Val k equals fn of x, same thing, fn of y. So adding 1 and 2 is a function that adds 1 to a function that takes 2 and produces an output that adds 1 and 2. But here we have a function that takes the first argument and then gives that to the function that takes the second argument. And returns the output of just giving back the first argument. It still feels confusing. Of course, this does not say anything about. It's almost like you want to see the values provided inside of here, but this is the definition, this is the body of the function, what the function does. And again, I think it has to do with a mix-up. Like we expect that the body of the function will somehow be polluted with some sort of state that comes from the values that we provided to it. So almost like the function of the y, so almost like I expect the y to be here, but only I get the x. f and x, f and y, x. Val k, f and x, f and y is x. Val always 42 is k42. Right, so what would be the difference? Look at this. You could say always 42 equals 42, right? And we have always 42. But you could do well always 42, 43, let's call it, equals k 43. What's happening? Valued restrictions are instantiated to dummy types. Didn't I define k? K. I did. Fn val k, fn x, fn y, x. But maybe because I didn't provide it the second argument. Interesting. Is k42. This doesn't work. 42 equals k42. Interesting. So constants is about behavior, not time. Yes. Conflating the constant combinator's behavior with the idea of immutability across time. That's not true. A constant function does not mean the function or its result persist unchanged. Always hello, k hello. Why does this actually... because of the value restriction, the expression k42 is not treated as syntactic value, and the SML type system prevents it from being generalized. Why does it prevent it from being generalized? So the constant combinator k is defined as val k, fn x, fn y, x. So what's its type? Right, a, b, a. So that should take an int or a string. It's polymorphic, that's the meaning, and can take arguments of any type, A and B. So when you partially apply k with 42, the resulting expression is equivalent to f and y 42. However, this is the result of a function application, and SML's value restriction disallows the generalization of the type variables for such expressions unless they are syntactic values. Use the fun keyword. Oh, a placeholder. Always 42 is now syntactically a value. Val always 42, fn. But I want to use the k combinator. Yeah, this is kind of confusing. Yeah, if I give it ignored, then it would work. This does not work. But this works. This works, yes. It expects the second argument because it takes the first. Yeah, I'm just trying to, redefine it. Now k is recognized as the proper value. So it says like that you could define a bool. Val bool. Boolean. Let's try to do this, like even with an if statement. If fn no, if true, yeah, it would be interesting because it gives us the first argument. How would you define a boolean with a k combinator? Well, yes, we already have it, right? K1 and 2, it gives us 1, so k true and false. True. Okay, it already has a bool, but you could do like true, well, you could bind 1. I remember, what's his name? David Beazley. That would be nice to check. Beazley and Lambda Calculus. I think he did a course with Lambda Calculus, a really long one. I remember seeing that one time. And he began like really, in a nice way. Yeah, it's really long. 3 hours and 26 minutes. Ooh, Lambda Calculus from the ground up. I might actually watch this. What's the time? 32 minutes. Maybe I could watch this.
Welcome everybody to this. This is the Lambda Calculus tutorial. Hopefully you read the description of this, especially the part about nothing usefully practical being done in here. So if you're expecting something that you're going to be able to use at work, probably in the wrong place. Also, just a couple of little logistic things. You will get the most out of this by typing along and trying the code out as we go and experimenting. And I will also emphasize that almost nothing is obvious in here. So I want you to meet your neighbor at the table there and feel free to chat back and forth, what is he talking about? And what are you doing? You're gonna get more by trying stuff out, talking with each other. I also have an assistant, Brian Ward, in the back with a traveling microphone. So if you have a question or something, just to make it a little bit easier for you people to maybe raise your hand, and he'll come find you, and you can ask the question. Little background on the tutorial. We're going to be talking about the Python's Lambda function a lot. Okay, so you've probably seen things like this before, hopefully. One thing about Lambda is that it is a way of defining a function in Python. It's just another way of defining a function. And one kind of interesting challenge with Lambda is how to introduce it when teaching Python. I actually teach a lot of Python classes. And this is something that usually comes up at some point, maybe with the sort function or something. And it's oh, you use the Lambda function. And then you have to sort of describe this to people. I think that, we have Stuart here who's taught a lot of classes, and one question that sometimes comes out is why is it called lambda? I don't know, does anybody like encounter this in either like just teaching Python to people or anything? I mean, it's kind of a weird name, right? It's like lambda. I'm like, what's that about? And then you start answering that. It's like, well, it's called lambda because everybody else calls it lambda, which is sort of a non-answer, right? That's just like deflecting to some, non-thing. And then people are going to ask, like, well, why does everybody else call it lambda? And then it's like, well, they called it lambda.
What is he showing? Wait, is this still encoding? Okay. Fnx. Will he say f is, that will be val f equals fn of x. Lambda x. Okay, so the column would be fnx, and now the column actually lambda x dot and 3 times x plus 1. That's what he's saying actually. So now we can do, he's calling f of 2. He gets 7 back. Okay.
Lambda in Lisp or Scheme or something. Okay, so it comes from Lisp, and then it's like, well, why did they call it lambda? And it's like, well, they took it from the Lambda Calculus. And then if somebody asks, like, what's the Lambda Calculus, then you start like running away and like horror. And actually just like personally, before doing this tutorial, it's like I didn't even really know the Lambda Calculus at all. I mean, I think I'd crossed paths with it in graduate school at some point, but at the time that I did it, I was studying for qualifying exams and spending the other half of my time playing like Duke Nukem or something like that. And like my memory of like the Lambda Calculus was just 0. So this tutorial is kind of born out of that. It's like, what is Lambda Calculus? And like, I don't know, how does it work? I think it's going to be really cool. I mean, my experience with it is like, this is just insane and crazy, and I think it'll be fun. So that's what we're going to talk about, and I'm going to kind of step you through it in sort of maybe an unusual way. But the thing that I wanted to start with is actually that thing that I got up on the slide, the lambda x there. How would you teach what's happening there to like a 10-year-old? I have a 10-year-old kid. He's taken, he's in 3rd, 4th grade. They're doing math. If you want to forget the lambda part of that for a second, but like just if you were to describe just like how a function works, what's going on there? Like how would you teach that? Yeah. Yeah.
Kind of along with those, right? If you have the 3x plus 1, like that's a function that you'll see in math class. But the lambda is usually like an unnamed function.
Yeah.
Like in school, functions almost never have names unless it's like a sign.
Yeah. But it's not even about the name. Like if you're just if you have like a 10-year-old and you're just saying like f of 4, like what do you do there? You just it may be overthinking. It's like you just replace the x. I mean, like if you were to describe like what that does, it's like you replace the x with 4.
It's kind of cool. The book that I'm doing from Greg Michelson, he uses the same word, replace, instead of lambda or like a function. So when he has a very good book. So the Lambda Calculus book and Elementary ML. So in the first chapter, he's showing like how to program, but not with syntax like we know it, right? Just with words, like pseudocode. But he's using exactly the word replace. It's kind of cool that David also does the same thing.
And then you do math, like it's like 3 times 4 plus 1. And you sort of describe the function as like, well, the whole thing that's just going on there is you just replace the x function, substitute the x. There's some interesting things that you could get into with like a kid, like if you said like, well, what if you have f2 plus 3? Like, how does that work? There's their issue. It's like, Okay, but you're going to get 16, but like, do you do the 2 plus 3 first? Like, do you get 3 times 5 plus 1? Is that how you do that? Or do you have, do you do that? Like, do you just literally take like the 2 plus 3 and like plug it in for the act? And there are some variations there, but basically function, you take the thing in parentheses and you substitute the act. Okay, so you have that. Now, the thing that we're gonna start with is what if you were teaching programming and you decided right at this point to stop, saying you don't need to know anything else. Okay, so what if you had this sort of thought experiment where it's like you actually do not need anything else other than substituting the act. So imagine that you had Python. Okay, so you're going to do like the scene from like the Holy Grail on Python, and you're going to like start chopping things away from Python, like non-essential parts of Python. I'll help you out here, like no packages or modules. That would solve a lot of problems, right? You get rid of that. What if you had like no objects? Or no numbers? Or no strings? Or no data types? You just basically just like start carving it away. Or you just start stripping things down, and it's like how much of it could you actually cut away and still actually have something that you could compute with? Like do anything useful. And the thing that we're gonna talk about here is actually an idea, which is what if functions are actually the only thing in the universe, and not only functions but just single argument functions, and nothing else exists. So you can write a function like you can say f of x, and you can have that, but you're not allowed to do anything else in your whole language. Now this is going to get a little bit mind-bending because you're thinking of function like if you said return x plus 1, no, there's no numbers. Okay, so and there's no plus either. We don't have any operator. Okay, so that's a little weird. You can't do this because we only have single argument function. This actually solves a lot of problems, by the way, because if you only have one argument, you don't need defaults or keywords or positional only arguments or anything. Like if you're following that debate, it sort of collapses. Yeah. So you can't have multiple arguments. You could do something like that, but it's hard to decide whether that's very useful. It's sort of under-specified, right? I mean, you could have a function x, takes an x and returns x.
The functions always have to take arguments?
They always take an argument. So zero argument functions are not allowed. Yeah. There's no if statements. There's no. We got rid of control flow. I didn't put it on the list, but control flow. I mean, once you start thinking about control flow, it's going to lead to things like exceptions and all that's evil. No, we don't want, no. So yeah, control flow is gone. The only thing that you have is basically simple argument function. You could do things like this. That's okay. X is a function. The reason it's a function is because functions are the only thing that exists in the whole universe. So by default, it has to be a function. Not clear what that does. You could also create a function. I mean, this is technically allowed. I mean, you could do something like that. It's a little strange, but I mean, you can.
So define f of x, define g of y, return x of y, return g. This is interesting. Return x of y, return g. Define f of x. Yeah, how would you do this actually? So val x, val f of x. Well, I guess we don't need the def, We could just do fn of x and fn of g. No. No, 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 no. Interesting. He's actually giving it a name. Val f of x. Val f. No. So what did he first do? F of x, return x. Did he give it a name? He gave it a name. This was not an anonymous lambda function. Was that an anonymous lambda function in Python? I guess we're trying to def f. Yeah. David Beazley Python course on Lambda Calculus. And he shows one example. So let's do Python. Where is it now? Let's do it here. Def f of x. Def f of x. Def f of x. And def g of y. Oh, def f of x. Def g of y. Return x, y, return g. Yeah, I don't really get this. Return x, y. Return g. Can you explain what's happening and show the same in SML? Yeah, that was kind of higher order functions. Oh, he's using where one function returns another function. Def f of x, def g of y, return x of y, return g. F is a function that takes a single argument x, yes. The argument x is expected to be a callable another function, definition of g of y. So inside f, the function g is defined, which takes an argument y. G of y applies the function x provided to f to y. Oh, it just provides it. Yeah, I was confused by this. Yeah, you could do like a and b and return a plus b. But what's the second one? It returns g, the inner function. When f of x is called, it remembers x via closure and returns a specialized version of g. H is now a function g of y where x is double. Result h of 10, double, print output 20. Fun f of x, let fun g of y is x, y, and g. F is a higher order function that takes an argument x, g of y. G is a nested function inside f, it takes an argument y. Let's use this f function with a doubling function. Fun double z is z times 2, val h, f double. H is now a function where x is double. Val result is h10. H10 calls g10, which returns double. Yeah, I kinda don't get this really. Well, I'll return to this.
You could have a function that defines a new single argument function only. Okay, it has to be single argument. The only thing that you can do with a function is call a function. Keep in mind, we have no numbers or operators or anything other than just calling a function, and you could return that. So you can do this sort of stuff, but now that the challenge is, could you actually do anything with that? Okay, I mean, again, kind of mad. You've taken Python, you've just chopped everything off of it except for functions, single argument functions. Is there any like thing in the real world of any kind, anything that you can do with this like programming restriction? So I'm going to let you ponder that for a couple of minutes here. It's a little tough, I think. Well, and, you know, I'm trying to gauge whether anybody has any thoughts on zero thought. Yeah, it's the thing that's a little weird about it is it feels like extremely abstract at this point. Like, keep in mind, like, did we just lose audio for a second? Do you have audio back there? I think we lost audio. Do you have audio? You're getting audio in the recording? Okay, maybe it's just the speaker. Okay. No, the thing, it's like at this point, it actually feels like very, very weirdly abstract. I mean, just to emphasize, in this system, there is literally nothing other than a single argument function. There are no bits or anything. Yeah. As long as you can return a single argument function. Actually, that's an interesting, like, multiple things, like, that would imply the existence of a data structure or something like a tuple. So as long as your multiple things is a single argument function. Functions can be passed around, yes. So you can pass functions, you can turn functions, as long as they're single argument functions.
The feeling is that you could end up with something magnificent and Turing complete if only you could pass one thing in at the very beginning. You know, then you could have.
Well, as long as it's a function,
yeah,
right? Yeah. No, it's a real brain. Maybe one way to think about this is it's like a weird escape room that I've put you in. From coding, it's like, okay, we got this style guide, which is extremely easy to remember because single argument functions. That's it. But the question is, like, how do you do anything with it? So.
You have a namespace.
Actually, names are not technically allowed either, but I'm going to break that rule just to be able to do anything. No. It turns out that having names of like global variables is not really technically allowed either, but we're gonna lighten that rule. So, all right. So in looking at this, okay. So at first glance, it's going to be like, this is just okay. I don't even know where to start with this, and so. So I thought I would start you with actually something real that you could model with this. It's going to be something really unexpected, I think, but you could model a switch using this. I was trying to think about how to make the tutorial go full stack down to the bare metal. Basically, you got to talk about electricity and other things. So let's say you have like a switch like that. Okay, so this is a switch, like left, right. It has two inputs, A and B. It has an output on that. That is actually something that you could model in this system. But the way it's going to work is going to be a little strange, okay? I'm going to write a function left that takes in a single argument because everything has to take single argument. and then inside, whoa, okay, hot audio excitement there. I'm going to define a function f that returns the A, and then I return the function back. Now, at first glance, that's going to look really weird. I'm going to write a function right that does the same thing. Well, almost the same thing. Okay, so I'm gonna have you type that in.
No, this is like defining a bool. Well, but he names it left and right. It's kind of cool. But how will we do this in SML? Val left. Let's call it left. Well, left of x. Maybe left of x. Well, I could use lambda functions, so I don't even need to do, well, left equals fn of x is f of b, return a. Well, maybe fn x, it should return y, but this wouldn't work, right? Return f, return a, return f. I think this is fn y, return x. And val right, fn x, fn y, return y. So now if we do left 1 and 2, we got a 1. It's a left. And right 1 and 2, or 1 and 2, we got a 2. So now we used actually the constant combinator. That's what he used. It's so weird. Def left, def fb, return a, return f. I guess the way Python does this, it's kind of confusing. I find this much more intuitive. fnx, fnyx. What does he do? Def, okay, that's like left a, that's like fnx, def and f, well that's like fnx, fn, lambda a, lambda x, lambda b, return lambda a, return a. It's just he had to do return f also as well. Why did he return f also? Okay.
Now how this is going to work is this is essentially like a chaining of functions where you provide like an argument to the first, like the outer function. You say like, okay, left, A, that's 5 volts or something. Okay, think electricity. And then what it is doing is returning a function back. Like it's returning this F back.
But you have a string in there.
Yeah. Well, okay, yeah, well, ignore that for the moment. No, ignore that, no. Yeah, I'm breaking the rules a little bit, but you're onto something important here in a second. Okay, so what's happening is like 2 inputs are coming in. There's like an A, which is like the 5 volts, and then the B is like maybe ground or something. And what left is doing is it picks out the A, basically. Like if you're in the left position, it means that you're picking the A. You're connected to the A. And if you were to do the same thing with like the right function, it would come back and it would say, well, you're connected to the ground. Now, the thing that's kind of wild about this is that these functions, they don't really represent like a thing. It's not a bit. It's not a piece of data or anything. What they're representing is a behavior, basically. Like the behavior of left means that you're connected to the A. And the behavior of the right means you're connected to the B. In some sense, it doesn't really care what you pass in here. Like, I mean, like you could have left of loud, like maybe like loud soft or something. If you're in the left, it means you're loud. If you're right, it means you're soft. It's still a little, it's still a little abstract, but essentially you've got, you're modeling, again, like a behavior. It's like the behavior of a switch is that if it's in the left position, you're connected to the A input. And if you're in the right position, you're connected to the B input. And that's what is, what is happening here. Let me just pause for a second. Again, I definitely want you to try typing in the code as we go and trying this stuff out. So give you a minute to try that. I do, while you're doing that, by the way, I do want to make a mention that this technique that we're doing here, okay, this is not part of our system, but this technique of writing single argument functions, like let's say you had a function add, like that, where it took 2 arguments. You could rewrite that in a really funny way. Using single arguments. This is not going to win you points at work, doing some trick like that, but you can take like multiple argument functions and turn them into single argument functions. This is something known as currying. If you've ever heard that term before, it's sometimes something people will throw around that term. It's basically a way of like you can take like multiple argument functions and just kind of turn them into single argument functions. Again, you're going to have a lot of explaining to do at a code review if you were to show up with something like that normally, but that's what's happening there. All right, how are people doing? Questions? Okay, next thing we're going to talk about is, could you take that and spin it into the notion of truth? Most computers do have a notion of Boolean values, right? Like you have true and false. Could you represent like true and false using this scheme in some way? And the reason that I kind of did the switch example is that you could think about it like that. Like think about your computer. What is a true value on your computer? It's an electrical device, right? I mean, it's electricity flowing around, and there, what is true? Yeah, something. I mean, it's like a bit on your computer. What is a bit? I mean, is it like, it's probably like, it's either like 5 volts or 3 volts or something. I mean, it's like there's electricity on it, or it's the ground. It's one or the other. And it turns out that maybe that switch code that we had is the same thing that we could kind of do for true and false. I'm gonna switch over to Lambda there just to shorten the syntax a little bit, shorten the amount of typing. So maybe true and false are kind of the same thing. Basically, what true is it's like a behavior. Basically, true means that you're connected to the first value, whatever it is, 5 volts or something. If we're talking about computers again, and false is the opposite. It's kind of arbitrary in a way. I mean, but if you think about like true and false value.
It's funny he didn't pass its def true x, return lambda y x, and lambda y y. It's like you don't almost see 2 functions. But that should be the k combinator. Val true, lambda x, right? You can't do just this. Y. Can you? No. Unbound variable. But yeah, he's saying val true x equals fn of y. Fn of y x. Really? Will this work? No, right? Val true equals actually should be lambda x takes an x and gives back the function that takes a y and gives back the output of x. And val false, same thing. Lambda x, lambda y, but this time it gives back the y. So now when we do true, 5 volts and ground, we get 5 volts.
It's like you have true and you have false, and true is supposed to be the opposite of false. I'm never quite sure with the news these days, but you know, but like normally, like true and false are meant to be opposites, and that's kind of what's going on here. You've got x and y, true and false. Like true is one of them, and false is the other one. And again, it's a little odd because we're not representing true and false as a concrete thing. It's not a bit. It's not a piece of data, anything. It's strictly like a behavior. The behavior of true is that you're connected to the first thing, and the behavior of false is that you're connected to the second thing. Question up here is
I'm a little bothered by the absence of fact-finding.
fact-finding.
Yeah, it's like the thing where, you ask the reporter, are you sure there's cannibalism going on? He says, no, we're just reporting that there's cannibalism going on.
Right.
And so we have true as the left value, because it's still just a switch, and false is the right value. So the hair that stands up on my neck is that we won't, in some sense, be able to have the sort of fact-finding that you need to have an actual Boolean structure.
Yeah, there's like nothing concrete to really hang on to here. It's like true. I find this like really disturbing. It's like true is not a thing. It's just like, well, it's whatever the x is. That's what true is. But we haven't. But the only thing that we know about the rules here is that technically it has to be a single argument function. These values like 5 volts and ground, that's bogus. They normally can't do that. So, I mean, like normally I would have to do something like this. I'd have to say, well, you can do true and false, or something like that would be okay. Or you could have a function of one argument, like you could say lambda f, x is x. I mean, I could say true of f.
I don't know. I just don't find it that disturbing because, yeah, of course you have true or false or left or right, but it depends on the context, right? You always have to provide some kind of scope. Within that scope, something can be true or false. But I guess what they're saying is that the meaning of true is same as false or true. Well, then you can get really philosophical about this. Like, what's true and false? Like, you could say false and mean true, and say true and mean false. But that brings to the point that it's about context. Yeah.
False or like, but that is like making my head explode because it's like it feels like even more ungrounded than it was before, right? Doing that. So it's very weird. It gets even weirder if I challenge you to start implementing the Boolean operators like not, or, and or. Let me take that away. Here's a challenge. Like, how could you define not? And just to be clear about the behavior of not true is basically false.
How would we do that? How would we define not? Well, not is almost like a combinator of sorts that also gives back the first. But it's almost like an after step. So if I give it true or false, not gives the opposite of what was given. The opposite of what was given. So does that mean that it ignores the second? That's interesting. So the constant ignores the second output, the second input, and gives back the first input. And the not operator, what does it do? So we have true, and we have true, true. Can we do this? True and true. Not true. Yeah, interesting. Well, false. False. What does false give us back? Nothing. Well, you could do false true. I can't. Right, I can do only false true. No, I can't. Oh. Wait a second. True of true and false. No. What did we define actually? True. 1 and 2, right? And it gives back 1. And false, 1 and 2, it gives back 2. So true, I guess you could do it like this, right? Gives back true. But this should turn it around. It's almost like saying false. True and false gives back false. But we have to give it 2 arguments. This would be a function that would take 1 argument and give out another function that gives the opposite. How would you define not? Well, that's interesting. Not true. Right, we have it already defined here, I think. Not true. It's false. Not false. True. Maybe we can check the type of true. That doesn't work. Let's check this out again.
And not false is basically true. At least it was the last time I checked anyway. So, yeah, Brian, you want to try to get people to do the mic on the question here? Yeah.
So just to sort of keep inventory here, are you cheating again here for narrative purposes at the end, or do we have a universe that has identity?
I'm cheating with Python here.
Okay.
No, the assert statement is that's some Python stuff. Yeah. It becomes a little bit hard to talk about if there's if there's literally nothing, but it's. So the question is, how in the world would you do not? And this is where things are going to. I mean, it's already probably very abstract and weird. I mean, it's like wait.
But I don't. Yeah, you could do like with a conditional, but we don't have conditionals, right? If true, then true, right? Like this, but it's a string then. True, else, false. Yeah, you could do like val not is if true. If true, then false, else true. Yeah, like this. So not. Wait, let's do my not. If true, then false, else true. So my not true. My not true. Yeah.
It's like true and false are functions, and like, and what does it mean? And so like, let's think about the not for a second. The only thing that exists in this universe is function. So one thing that we can.
The only thing that exists is a function, right? So let's try this. Come on, val not, my not. No, actually, let's call it not equals what? Fn of x, a lambda x. It's a function that takes an input, an x, which will be, for example, true, and gives back the output. So now we have another function, fn of y, gives back a function. But fn of y would mean a second argument. We don't have a second argument. So to not, we don't give two arguments. So it will not take a second. So the fn of x and returns a y. Really? But this wouldn't work. What's a y? In moments like these, it's kind of cool. Wait a second. F11, actually. Let's go to ChatGPT. So I'm trying to define a not boolean operator, but I'm having difficulties. I have to use just lambdas. I have to use just lambdas. Wait a second. Don't tell me, but guide me. Maybe it's too hard to guide this, you know. I want to think about it. Let's break it down step by step so you can discover a solution yourself. Understand the problem. A boolean not operator flips the value. So yeah, it takes one argument, right? So if the input is true, it outputs false. If the input is false, it outputs true. So booleans can be represented in lambda calculus as functions. True, lambda x, lambda y, x, chooses the second argument. False, lambda x, lambda y, y. That's what we did. Think about how true and false behave as functions, how much you use these definitions to flip their behavior. Lambda x dot lambda x, lambda y, x chooses the first argument. To implement not, you need to create a lambda function that takes a boolean function and returns the opposite. Start by thinking about how you could use the input's boolean behavior, choosing between two arguments to control the output. Try typing down a lambda function and testing it with true and false. Does it return the opposite as expected? Well, it didn't really help me, maybe because there's not much to help. Val not, lambda x. Really, it's not this, lambda y. It doesn't take the second argument. It should be the other switch, right? Otherwise, this is going to just, no, lambda x. How do you say the opposite? You see the problem. The problem for me is that it seems it's an single argument function that takes true and outputs false. But how does it know what to output if the input can be any of the two things? You see the problem? Because I cannot just write it has to flip it. It cannot just write something back. Booleans are behaviors. True and false are not just values but functions with specific behaviors. True, lambda x, lambda y, x selects the first, lambda x, lambda y, y selects the second. When you pass one of these Boolean functions to another function, you're leveraging their behavior. If you pass true, a pair of arguments, it always picks the first. If you pass false, a pair of arguments, it always picks the second. So using their behavior, the not operator doesn't need to know whether the input is true or false. Instead, it leverages their behavior. When true is passed to not, not should return something that behaves like false. And when false is passed to not, not should return something that behaves like true. Yeah, it's almost like I'm holding on to this concrete idea that, you know, it has to be something true, but is he saying also it's about behavior? Think about how you can use the input's behavior, choosing between two arguments to decide what the output is. What arguments could you give to the input Boolean to invert its behavior? What does true do when given two arguments? How would you make it return the opposite? How would false behave if given the same two arguments? What happens if you pass true to your not? Think of not as a higher order function. It can supply arguments to the input Boolean to determine its output. You don't need to explicitly know the input, you let it decide based on the arguments you provide. Yeah. I keep on defining the true, and val not is what? It's just the true. Not true. Well, maybe because I'm defining it with lambda functions, maybe because I already defined true. Fn x. Maybe because I already defined true. Fn of true equals false. Could I do this? Fn true equals false. I'm not sure, and val not. Val Fn true equals false. And FL false equals what? True. I don't have conditionals. That's not true. So not true returns false. And not false returns false. No, that's not correct. Yeah.
Can say about not is that x is definitely a function. Okay, we know it's a function because that's the only thing that exists. So that we have 100% guarantee that it's a function. Okay, so we know that it's going to be a function. The other thing that we know is that if our intent is to pass true and false to that thing, those are functions that have the two arguments. Remember, the behavior of true is that you choose the first thing, and the behavior of false is you choose the second thing. So we know that we can do this. Like we say, return x something, and then something else. And exactly right. So comment up here, just reverse it. So if x is true, what you want to do is pick out false. Like the behavior of true is you pick the first thing. And if it's false, you pick out the second thing. So not true is false. And not false is true. Okay? So
yeah, this is very simple, but it's not. It's not. Val not. Well, Fn of x. X false. True. But he's not doing this. Fn of y. Yeah, I have no idea. Okay, show me the solution in SML. But that's what I did. True and false, and not FNB, FNX, FNY, BYX. Oh yeah, I wouldn't know this actually. Interesting, it's not what he did. the booleans true and false. True chooses the first argument, true x, y, x. False chooses the second argument, false x, y, y. So not is a function that takes a boolean function b as its input. It takes the function b. Yes, I was not thinking straight. I was thinking as it takes true or false, but it takes a function that as its input, it takes a function which is a boolean, and it swaps the order of the arguments. Oh, byx instead of bxy, so it swaps. This effectively flips the behavior. If b is true, byx evaluates to y. If b is false, byx evaluates to x. Not true outputs false, not false outputs true. Okay, but if b is true, then how is b flipping two arguments? Where is the second argument? In the definition of not, let's do again. So fn of b. So not is a function. So the definition itself starts with the definition of not. I was going from my previous definition. Fnb equals lambda b, lambda x, lambda y equals outputs b x y, no, b y x. Yeah, it should be like that, right? The function not takes a single argument b. It takes a single argument b, which is either true or false. Then not returns a function that takes two arguments, x and y. But the function itself returns a function that takes two arguments, and this takes single argument b. Finally, it applies b to the arguments in reversed order, byx. B is true, defined as fnx, fnyx. If you call true yx, it will select the first argument, which is in this case y. Not true equals not true. Function x, fny, true yx in fnx, fny, y. The arguments x and y come from the context in which you apply the not function. For example, val test1 not true 1 0. Not true fnx, fny true yx. Yeah, this is kind of complicated. So, is not some kind of combinator? It looks complex. Takes only other functions as inputs, returns a new function as output, operates without referring to any external variables. Identity, operator, combinator, not as a combinator. Behaves like a combinator. It takes a boolean function as input, it manipulates how that function applies its arguments. Flips the order, negating its behavior. To solidify this, let's compare not to a famous combinator, the flip combinator. Flip takes a function f and reverses the order of its arguments, lambda f, lambda x, lambda y, fyx. So not is a flip. Not is essentially a specialized version of flip applied to the Boolean combinators true and false. Why is not a combinator? It's not a combinator. Is not a combinator. Is boolean not. Yeah, Google. That's interesting. Combinator. So what kind of combinator? I thought there are a default number of combinators, or like basic combinators. I'm still having difficulties understanding the not operator. Identity, constant, apply. It applies a function to an argument, lambda f, lambda x, f of x. Flip, also called a commutator or flip combinator, takes a function and flips its arguments. Substitution as a derived combinator. It's not one of the basic combinators like IKS, but it can be constructed using them. It specializes in negating Boolean behavior. So it's same as flip, but applied specifically to Booleans. Where, let's look at this again.
Oh, looks a little strange. Leave that up there. Gets a bit more interesting if you start thinking about and an or function.
Oh.
What if you wanted to have something like that?
Well. So not true. Not true. Error operator not. Didn't I define true? Value restrictions are instantiated. I think that's the thing with SML. Not true. I defined true already. Yeah, and if I do 1, 2, gives 1. So I guess I have to do not true. True? No. Well, you define a value that is not a function. Doesn't look like fn. The compiler cannot generalize its type without specific context. This is due to the value restriction rule, which prevents ambiguous behavior in certain situations. involving polymorphism. Val A, ref. Your case not true. When you write not true, SMS tries to evaluate it as not true. Fnx, Fny. True, Yx. Here the x and y arguments aren't fully applied, so the compiler encounters issues generalizing the type. Oh, I see. Because we didn't... I wanted to flip the true, but true takes... It's funny. True takes, like from 1 or 2, true takes the first. But so when we do not true, what? It does not have the x or the y. Ensure that you provide enough context for SML to infer the types correctly. Fully apply the function. Output 0, false. So when we do not true 1, 0, not true 1, 2, we get 2. Oh, because otherwise we would get 1, 2. Look at this, 1, 2 we get 1, but not true 1, 2 we get 2. So you could say true, true, false. We get true, but not true, true, false. We get false. All right. Declare the types explicitly. If you don't want to immediately apply all arguments, you can give not a specific type annotation to help SML. Val not is a type of a function from an A, a B to C. A, B, A. And then it flips it, B, A, C, FNB, FNX. Okay. Test 1, 0, output false. Interesting. Interesting, interesting. It's funny, like SML looks so nice compared to Python. Actually, it's so weird. Some things, you know, take off and some things don't. Oh, we're supposed to define and. So I think I have now more context to define and. So right, we had val not. Let's do again. My not. Wait a second. I think we have to do this. So let's try again. Val true is a lambda x, lambda y, x, right? And val false equals lambda x, lambda y, y. And then we define not as lambda b, right? Lambda x, lambda y. And now we have b, not x, y, but we be y and x. So how would we define and? And would be, what does and do? And checks. If there is true and true, it gives back true. And if there is false, okay. Guide me now in defining and in a similar way. So yeah, I wanted to see this. So the Boolean AND operator has the following truth table. True, true, true. True, false, false. False, true, false. False, false, false. Oh, this is interesting. I keep thinking of, pattern matching. But how would you do this only with lambdas? Wow. In essence, and true B should return B, whatever the second output is. And false B should always return false, regardless of B. Okay, he's always extracting the main meaning. Like, if the two inputs are the same, we get the same back, actually. True B should return B. What does this mean? True B to false B. Well, if we get true and true, we get true, right? So, and we get false and false, we get false. So if both inputs are the same, we get the same input back. But what are the other cases? If we have true and false, we get false. And if we get false and true, we get false. So there are two things. If the inputs are different, we get false. And it makes no difference if it's xy or yx. So if two inputs are different, we get false. If they're the same, we get whatever they are. So the result of AND depends on the first input, true or false. If the first input is true, the result depends on the second input. If the first input is false, the result is always false. Now think, how can you use the behavior of true and false as functions to achieve this? Remember, lambda x, well, true. Gosh, I have no idea this seems like now a mountain. I would have to go through this, break it down. So AND will take two inputs. Yes, AND takes two inputs. So val AND equals fn x. But wait a second. Does it take fn x? Or will, since not took b, will AND take a and b? AND will take two inputs, A, first boolean, and B, second boolean. It will need to evaluate A first to decide whether to return B or false. Think functionally. If A is true, it should pass through B. If A is false, it should ignore B and return false. How can you make A decide between B and false based on its behavior? Draft a lambda expression. A and is, alpha A, f on A, and lambda B. That's what I got. Lambda A, lambda B. But now what? Lambda x. Let's do this like this. Oh. Val and equals, let's do it like this, fn A, fn B. It's funny, I can see how I would do this with conditionals, but I have no conditionals. It's like I'm so stuck because I can't use conditionals because we have no conditionals yet. We are defining our lambdas from ground up. The challenge here is that we are building everything from the ground up. We can't rely on conditionals. We have no control flow. We haven't defined them yet. But the beauty of lambda calculus is that we can express conditional logic using the behavior of the boolean functions themselves. Let me guide you step by step. Toward constructing AND without using any conditionals, we need to define AND as a lambda function. Yes, A, the first boolean, is a function that can choose between two options. You can use A to decide between returning B or always returning false, and analyzing the role of A. If A is true, chooses the first argument and should return B. This means the output depends on the second argument. If A is true, chooses the first argument and should return B. This means the output depends on the second argument. If A is false, chooses the second and should return false. This means the output ignores the second argument and always picks false. So the role of A is to choose between B and false. This is where the chooser behavior of true and false comes in handy. Here's the key. You pass B as the first argument. Yeah, I can't think now. I can just stare at it and wait.
I'm gonna let you ponder this one for a second. I'm gonna give you a little hint on this one. One hint here is to understand how Python does and ors. So if I were to say 2 and 3 in Python, keep in mind this is not allowed in our system because we have no numbers, but we're just talking about Python here. What does that return? So that returns 3. But what about 0 and 3? What if I were to do 0 and 3? What does that return? You're kind of seeing like a hint of how to do this from Python. Basically, if the first item in AND is a true value, Python goes to the second value and uses that to determine the result. Like if the first thing is true, the only way you know whether it's like true or false is to look at the second value. If the first thing is false, like 0.
Yeah, I think I'm gonna stop now and read about
then you're just done. You know that it's false. So like what comes back is 0.
Read about George Bull or like something like that, you know. Booleans. Maybe try to understand them more in a Boolean data type. Data type. Generalities. Boolean. Yeah, I think I'll do some reading and, thinking. Bool. C++ Booleans. It's funny. How do you go like logic? Maybe Boolean logic, Boolean algebra. Yeah, I'll read this actually. Look at this. Claude Shannon observed that one could also apply the rules of Boolean algebra in this setting. And he introduced switching algebra as a way to analyze and design circuits by algebraic means in terms of logic gates. Shannon already had at his disposal the abstract mathematical apparatus, thus he cast his switching algebra as the two-element Boolean algebra, whose underlying set B is the Boolean domain 0 and 1. Interesting, two-element Boolean algebra. Yeah, I'll just do a bit of reading and see, what I come up with. I need a break.